Welcome back, class. So, you should have just watched a video on the nucleus, which outlined some of the basic ideas around atoms and different ways that atoms can be different and the same, things like isotopes, etc. So we're going to go over some of these ideas and emphasize some of these things in this lecture section here. So the first thing I want to do is talk about how we describe elements. Right? So how do we talk about elements? How do we, understand how elements are different or how they're the same, etc. Well, first, fundamentally, right, we have the name of the elements, right? Every element has a name, sodium, iron, lead, etc. Right? So we can describe elements by their name. More common is that we describe elements based on what's called their chemical symbol. Right? And so the chemical symbol is a 1 or 2 letter abbreviation. Right? So the chemical symbol is going to be a 1 or 2 letter abbreviation. And this is what we're going to find most commonly listed to identify the element, especially on the periodic table. So the periodic table is going to be our list of the elements, and most periodic tables will contain the chemical symbol, but many will not contain the name. So this is why it's so important to understand what these abbreviations are and what these symbols are, and to make the connection between the name and the symbol. And with that being said, while I am not going to require you to memorize the entire periodic table, all 118, 19 elements, there are some elements, it's roughly about 40 of them, that we do need to memorize the name and symbol. And yes, for those of you who might be wondering, right, spelling counts here for the names. And so, just so you can get a start on it, you will need to memorize the name and symbol, so just the name and the symbol, for the first 30 elements. So if you're looking on the periodic table, that would be element number 1, hydrogen, through element number 30, zinc. And then some selected other ones, right? We have Br, right, bromine. We have iodine, Kr, which is krypton, Xe, which is xenon. So these are some what we will call halogens, and these are a couple noble gases. We have Rb, rubidium, Cs, cesium, Sr, strontium, and Ba, barium. We have Ag, silver, Au, gold. We have lead, Pb, mercury, Hg, and Sn is tin. So we have these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 additional. So we have a total of here 43 elements that we need to know the name and the symbol. And then my guess is you probably know quite a few of these already. And so it's simply a matter of learning the ones we don't. Now, a couple things I'll point out is that when we write a symbol, if it is a 2-letter symbol, the first letter is capitalized, the second letter is not capitalized, right? So we don't ever want to write something like AU, right, as capital A, capital U, right? We have first letter capitalized, second letter not capitalized. Typically, when we write the names of elements, they are not capitalized when we're using them in a sentence. Okay, so we have the name and the chemical symbol and what we need to know about those. Now, another fundamental way that we describe an element is based on what's called its atomic number. which is simply the number of protons in the nucleus. Now, it turns out this is the unique identifier of an element. It is what makes an element what it is. So, for example, if I have oxygen, which has 8, atomic number 8, or has 8 protons, in order to be an oxygen atom, it must have 8 protons. So there is no such thing as an oxygen atom that doesn't have 8 protons. Just as there is no such thing as a beryllium atom here that has anything other than 4 protons, right? It is what, in some ways, Dalton was trying to get at, or was alluding to, in that all atoms of a given element are the same. And how they're the same is the number of protons in the nucleus. Now, once we know the number of protons, we've also established, right, something about the number of electrons. So, if we have a neutral atom, right, which atoms are, the electrons will equal the protons. So if I simply have an atom of beryllium with 4 protons, it must have 4 electrons. Or an oxygen atom with 8 protons must have 8 electrons, etc. So protons equal electrons. Now, what about neutrons? Well, these are a little trickier, right? We need to have a little bit more information about the atom here. We know that there are a certain number of neutrons in the nucleus. And the way that we are able to identify that is by knowing what's called the mass number. Right? So the mass number is simply the sum of the protons and the neutrons in the nucleus, or tells me the number of particles in the nucleus. And so the neutrons will simply equal the mass number minus the number of protons, or the mass number minus the atomic number, right, will give me the number of neutrons. And so, if I know what the element is, and I know its mass number, I can figure out how many protons it has, how many electrons it has, and how many neutrons it has. Because remember, you will know the atomic number because the atomic number is going to be listed on the periodic table, and you should always have access to a periodic table. So we're going to be able to know the atomic number as long as we know what the element is. And if we also know the mass number, right, we can figure out the number of neutrons. So the thought process goes is we know the protons from the atomic number. If we know the protons, we also know the electrons. And if we know the mass number, then we can figure out the number of neutrons. So, now we have some idea of different ways that we can describe the elements. We can describe them by their name, by their symbol, by their atomic number, right? These are the sort of the identifiers of the element. Now what we're going to find out is that we can also describe them in a little more detail based on their mass number. Because while Dalton was correct in all atoms of a given element are the same because they have the same number of protons, one thing that he was not quite right is all atoms of an element do not have the same mass. There is different versions of the element that have different masses based on how many neutrons they have. And this is what we refer to as isotopes. So isotopes are different versions of an element with different numbers of neutrons. Now, what's the difference between different isotopes of an element? Well, first of all, they will have different masses. Because having different numbers of neutrons will give us different masses. They will have the same number of protons. Right? So isotopes are the same element, so they must have the same number of protons. They only differ in the number of neutrons that they have. And they will have the same chemical properties. So, while Dalton observed, right, that all the atoms, of a certain element have different properties. Some carbon doesn't behave differently than other carbons, chemically speaking, right? And that's true. So all isotopes will behave the same in chemical reactions. So for the most part, for the chemistry, we don't really need to concern ourselves that much with what isotope is reacting, right? Now, we want to understand the existence of them, but we don't worry about having a given isotope in terms of how it will chemically react, because they all react the same. So, but let's look in a little bit more detail of how we can characterize these different isotopes. So if we take the example of neon here, right? Neon exists as 3 different isotopes. Neon 20, neon 21, neon 22, right? And so there's different ways that we abbreviate isotopes, what we call isotopic notation. The simplest way is simply to have the element name followed by the mass number. And so by doing this, right, if we know the mass number, again, that provides that additional piece of information that allows us to know the number of neutrons, because simply by knowing what the element is, we know how many protons, right? We know the atomic number from the periodic table. Now, there's a more formalized way where we can use the chemical symbol and we can put the mass number superscripted on the left and the atomic number subscripted on the left. So you get a notation that looks something like this, where neon 20, right, would have a mass number of 20 and an atomic number of 10. We can have neon 21, right? Notice the bottom here is the same on all of these because they all have the same number of protons. What's different is the mass number because the neutrons are different. So if we analyze these a little bit, we see that all versions of neon have 10 protons, but one version has 10 neutrons, another one has 11 neutrons, another one has 12 neutrons. So they are going to have fundamentally different mass numbers, and therefore they're going to have different masses, right? Because if you have different numbers of particles, those extra neutrons are going to contribute to more mass. Now, this natural abundance thing, well, it turns out that in nature, elements always exist with the same ratios of their various isotopes. So any sample of neon that I were to find would have 90.48% of neon 20, 0.27% neon 21, and 9.25% neon 22. So isotopes exist based on this natural abundance. So unless something has been done to artificially change this natural abundance, then it will exist according to whatever the natural abundance are for the isotopes of that element. And different elements have different numbers of isotopes and with various natural abundances. Okay, so now that we have an idea of what an isotope is, then what does this do to how much an atom weighs, right? So it would be that we could just, say, okay, I have an atom and it's going to have this mass. But now we have different versions of an atom that have different masses. So how do we put a mass on the periodic table, for example, right? A single mass, right? Well, we do an average mass. And this brings us to what's called the relative average mass. And these are the masses that we will find listed on the periodic table. And so the relative atomic mass is what's called the weighted average mass of an element based on the natural abundance of the isotopes. So essentially what we do is we take, if we want to determine the atomic mass, we take the mass of isotope 1 times its fraction, or its natural abundance, right, in terms of a fraction, plus mass of isotope 2 times its fraction. And we were to do that for each isotope. Right? And so this is a weighted average because we're taking into account what percentage of the isotope comes from this isotope, what percentage of the element comes from this isotope, and what percentage comes from this one, etc. Right? We can't just add up the masses and divide by 2 because it's not a 50-50 split, right? And so let's take this example. So if we're going to calculate the atomic mass of gallium here, we are going to take the mass of isotope 1. So we have gallium-69, right? So this is gallium with a mass number of 69, has a mass 68.9256 AMU, and it represents 60.11%. So as a fraction, we write that as 0.6011. Now we do the same thing for our second isotope, gallium-71, which has a mass of 70.9247 AMU times the fraction, so 0.3989 for that. So now we're going to see what is the contribution from each isotope to the overall average mass. So if we do this one, this comes out to be 41.431 AMU. This contributes 28.292 AMU. And if we add all this up, we get 69.723 AMU. And we're going to round this to 4 significant figures, or 2 decimal places, and that's a good guideline when we're working with these atomic masses based on these percentages. So we're going to take this to 69.72 AMU for the atomic mass of gallium. Now, if you were to look on the periodic table, you should see that the listed mass for gallium is indeed 69.72. And so what this value of 69.72 AMU represents is it represents the mass of an average atom of gallium. So this represents the mass of an average gallium atom. Now, one sort of interesting thing about this idea of atomic mass is that the other way to think about it is there is no actual atom of gallium that has this mass, right? All of the gallium will either have a mass of 68.9256 or a mass of 70.924. But by using this concept of the weighted average, we can have a number that would tell us, you know, if we take a huge sample of gallium atoms, right, an average atom would be represented by a mass of 69.72 AMUs, or atomic mass units. Okay, so the concept of atomic mass. So now we have all sorts of ways that we're characterizing these atoms, right? We have their name and their symbol. We have their atomic number, right? The number of protons. we can use this to determine the number of electrons, along with the mass number, which represents the number of particles, the number of protons and neutrons in the nucleus. And then this will allow us to determine the number of neutrons and talk about the existence of isotopes, right, which have various numbers of neutrons. And we can use the various isotopes that exist along with their abundance to calculate our average or relative atomic mass, which are the masses that we see listed on the periodic table. Now, one other sort of characteristic of atoms that we want to talk about is their ability to turn into ions. So an ion is simply a charged atom. Now, how do atoms become charged? Well, atomic charge, or ions, are created by the loss or gain of electrons. Now, it's important that we understand that it is electrons that are lost and gained, and only electrons, right? So we will not lose protons, we will not lose neutrons, we will lose electrons or gain electrons in order to form these various ions. Now, if we lose an electron, this creates a positively charged ion, which we call a cation. So this is characteristic of metals, right? Metals will lose electrons to have the same number of electrons as the nearest noble gas. So we see that elements over here on the positive, or on the left-hand side of the periodic table, along with other metals as well, will tend to lose these electrons so that they have extra protons, right? They have more protons than electrons, giving them an overall positive charge in the atom. And they're doing that so that they can have the same number of electrons as the nearest noble gas. So, for example, sodium, right? Element number 11, right, with 11 protons, will lose, or excuse me, with 11 protons, 11 electrons, will lose one electron to become like neon, right, which is right over here, which has 10 electrons. Now, the other thing that can happen is we can gain an electron to take on an overall negative charge, which we call an anion. And this is the behavior displayed by nonmetals. They will gain electrons to form negative ions with the same number of electrons as nearest noble gas. So, for example, fluorine, which has 9 electrons, atomic number 9, will gain 1 electron to become like neon and have 10. So it'll take on that negative 1 charge. whereas oxygen, which has only 8 electrons, will gain 2 or take on a -2 charge to become like neon. And so, in the course of chemical reactions, we will often see these neutral atoms take on charge or form ions in order to get to the same number of electrons as the nearest noble gas. As we move on here, in the next section, we're going to talk a little bit more in detail about the periodic table and how we can navigate the periodic table.